It should not come as much of a surprise to know that if you have a function that describes a rate of change, you should be able to figure out how much change has occurred. And hopefully you'll understand that better after watching this little video. But this isn't that tough to understand. If you know how fast something changes, you should be able to tell how much it's changed. We'll explain that more coming up here. But remember, the integral is the area under a curve, and that is understood with Riemann sums. Over here on the upper right, the definite integral from a to b is, by definition, it equals this limit. And I'll explain it once again. Hopefully you understand Riemann sums though. If you want to know down here in the lower right, if you want to know what is the area under that curve, and the area under the curve is the area between the curve and the x-axis, then it's hard to tell what that area is, but you can easily tell what areas of rectangles are. So to go from A to B, x equals A to x equals B, we want to know the area under the curve there. We'll split it up into a bunch of rectangles. And the delta x, if you do what is b minus a, that would be this distance right there. B minus a, you want to divide that up into however many rectangles you have. So we'll divide it up into, say, n rectangles. This will be the width of each rectangle. So you split it into 4 pieces. 1, 2, 3, 4. And so that is our change in x. That's the delta x. So delta x here is the width of the rectangle, and the height of the rectangle is, in this case, it's a left-hand Riemann sum, so the height is determined by plugging the x value into the function. And again, in this case, it's the x value on the left side. But you plug the x value into the function, and you get the height times the width. That's the area of the rectangle. You add all those up from the first one to the nth one, and as you get more and more rectangles, starting with n equals 4, then n equals 8, then down here n equals 16, then n equals 256, you can see the error is getting less and less and less. The limit as n approaches infinity, that's when you're going to get the exact area, or the limit means your error is going to go to 0. So that's the definition of the area under the curve, definition of a definite integral. Don't forget this idea of the formula. And its accumulation of change, it's as simple as dirt. So if you remember d equals r times t, I'll talk more about that in a minute. But here's a graph. Say this is your velocity. So the y is measured in miles per hour. Let's say you're driving down the highway. You start off from from 0, you speed up fairly quickly, and within 100, 120 seconds, 150 seconds, you're going around 75 miles an hour. So here we are, A is 300, B is 360. So this is 1 minute, and the height is going to be around 75 miles an hour. So it's a pretty constant speed. You should be able to get miles per hour. That's your height, and the width, we're measuring that in seconds. So times seconds. That should give you a total distance traveled. Of course, miles seconds per hour is a weird unit. We would have to multiply by the number of hours per second. And with that simple conversion, hours cancel, seconds cancel, that'll give us a number of miles. So you can see that graph is from this, and here we're going from A is around 300, B is around 360. Let's see, the base, it's actually 299.7 to 359.8, so it's 60.2 seconds. It's about 60 seconds, and the height is, if I click on that, 74.6 miles per hour. So the area of this rectangle is 4,490 and 66 hundredths. And again, the units on that are miles seconds per hour. And if we do that conversion, that gives us, we traveled a total distance of 1.25 miles. And again, 1.25 miles in 1 minute, going 75 miles an hour. That's how much our distance has changed. It doesn't tell us how far we've gone total. It just tells us how far we've gone from A to B, from 300 to 360 seconds. If our distance was different though, or excuse me, if our time was different, if we were going from say 90 to 150 seconds, then here it's harder to figure out that area. When this is curved, we have a problem finding out the area. But again, this area is how much distance, if you included this little error up here, this would be how much distance you've gone from 90 seconds to 150 seconds. And if you, again, looking at that curve like we were looking at, then this area can be represented by a Riemann sum, and the more rectangles you make, the higher n, the better the approximation is going to be. So getting back to this, hopefully you see how this area represents how much distance has accumulated while we've been going at this rate. Again, when the function is a rate, the area is the total change. It's the accumulation of change. So there's your simple as dirt formula. The distance equals rate times time. That's it. However, the time we're going to get is some how long we've been going, some delta t. In this case, delta t was 60 seconds. The rate is our function of time. And if you do the rate times time over some interval, well, and again, you add it up over some interval, that's going to give you your total change. So you call it distance, you call it change, I'll call it change. And I've got an example here. It's maybe a little bit of a morbid example, but it's definitely a timely example, because this function here, this is the function that most people are talking about nowadays when they say we need to flatten the curve. If you can handle 200 people per day entering the hospital, then you need to keep the curve down under that, and you wouldn't want the curve being way up here. So pushing the curve down and flattening it is the issue with the coronavirus. This is the projected curve for Florida. Notice the curve is a rate. It's deaths per day. It's not the number of deaths caused by corona, it's the number of deaths per day caused by corona in Florida. Back here, this is actual data, and then starting here on April, looks like I got this data on April 13th, I pulled it from this covid19.healthdata.org. The rest of this is projections based on their models. So trying to flatten that curve, these models are very complex. This is the stuff that they base this curve on. It looks like a nice bell-shaped curve. So, but if you think about the normal distribution from statistics, that's the bell-shaped curve. Here's the formula for a bell-shaped curve, and that's a pretty complicated exponential, right? It's e to the some power with x in it. So this is an exponential function, and it's a complicated exponential function. We're going to try to use a much simpler, just a quadratic, to describe this. So here's the quadratic that I came up with. It has basically the same values. Let me go back to this. This curve goes up to, I don't know, 140-ish, and somewhere early May is the peak. So if we go down to this new one, that would be on day, I don't know, 70-ish, 74 in here somewhere, and it goes up to 140, 150 maybe in there somewhere. So it's roughly the same model, but it is not nearly as accurate. It's not going to update itself automatically when we get new data into it, and but it's a nice simple model. Here's the formula. It's a fourth degree polynomial. We can work with that. Well, I think I called it a quadratic a few minutes ago, but again, fourth degree polynomial that we can work with. Take the derivative, you should be able to take the integral. Shouldn't be much of an issue dealing with simple polynomials like this. And when you take the integral, of course you get the area under the curve. And what that area under the curve will represent is, well, for example, if we start off right here, say going from day 60 to day 61, that's 1 day wide. And if on day 60 there were, what does this say, 120 deaths per day in Florida, then 120 times 1 will mean there's 120 deaths. And then the next day, from day 61 to day 62, on day 61 there were 120, whatever that is, 123 deaths per day. So times 1 day gives you the total number of deaths. And then again, from day 62 to day 63, there were this many deaths, whatever that is, 125, 126, times 1. That blue area represents the number of deaths total, not the number of deaths per day. And if we keep adding more area to that, we keep adding more deaths. And if we add up all these areas, we get the total number of deaths from day 60 to day 60, whatever this is, day 60 to day 64. The total number of deaths would be that area. And again, sorry for the morbidity of talking about deaths so much, but again, it's a pretty timely example. I'm hoping you agree. And if we took the integral of this from day 38, which is where the 0 is, on out to day 102, if we did that, we would get this total area under the curve here, and that would represent the total number of deaths from day 38 to day 102. It's how many deaths are accumulating. Again, because we have this rate. The function is a rate, and when you integrate a rate, you're accumulating the change. So that's the big idea. Deaths per day times day gives you number of deaths. A rate times, again, if it's a rate over time, a rate times time gives you the total number accumulated. I hope that helps. I've got an assignment for you based on this polynomial, this fourth degree polynomial, and here it is. Talk about when will the maximum number of deaths per day occur, and on down the list. The last one might be a little hard for you to turn in. You have to sketch the graph. My thinking is you can maybe sketch it and then take a picture of it and put the picture into your submission when you submit your answers online. There you go. Don't forget, my office hours for this class are Mondays and Wednesdays from 9 to 10, and I have Calc BC from 10:30 to 11:30 on Mondays and Wednesdays. I'm sure I can help you during those times too. And so far, from 10 to 10:30 on Mondays and Wednesdays, nobody's really come in for my geometry office hours. So basically, I'll be in my office hours from 9 until 11:30 on Monday and Wednesday. And then on Tuesday, Thursday, my office hours are from 1:30 to 3. Again, 1:30 to 2 is supposed to be geometry, but nobody shows up for that. 1:30 to 3 on Tuesdays and Thursdays. So go to meet.google.com and I'll be in the MHS math meeting if you want some help with this stuff. Let's talk about it.